Okay. So again, my name is Mark Skramstad, and I'll be running you through this hose selection webinar here. Oops. So a couple of quick notes. If you have questions, please ask them in the chat. There's a Q&A section where I will be going through at the end and answering questions. So it's also important to note that there's kind of a delay on this, so you can't really unmute yourself and talk. Again, throw it in the Q&A, and I'll get to it at the end. Again, my name is Mark Skramstad. I'm a sales engineer with Swageock, Minnesota, and I'll be running you through this. So really what this presentation is going to center around is selecting the right hose for the job. That's going to be the overarching theme. Within that, we're going to talk about some background on some hose types. That'll be kind of the first section. Also, we'll get into some common hose issues, specifically with routing and dynamic applications, and also some static dissipation within that as well. So next, after that, we'll get into some construction and sort of the effects that different construction methods have on performance. And without further ado, I'll get it going. So hose types. Here we see a typical hose assembly. So what you see is a core tube, which is the wetted components that fuels the media, that touches the media. You have the end connections with that, which is configurable, comes with a variety of options. We have the reinforcement, so we have a fiber braid in this case, and we also have a stainless steel braid in this case, and also a cover. So this looks like our S-series hose, which is a silicone cover. We do have other covers available, and like I said, we have other end connections available as well. So getting into just general hose categories, here we have metal. I'll just kind of run through these quickly. Metal, which has this corrugated, I think you guys can see my mouse here. It's got this corrugated stainless steel sort of core in there, and that corrugations allow that to be flexible. So that has a variety of applications where you really need that flexibility and that stainless steel. Second, we have this fluoropolymer, which is PTFE or a Teflon core hose. We were just kind of talking about that on the last slide. And then we also have these two, which we'll talk less about on the bottom two. So the first one being thermoplastic, which is often used in impulse pressure applications, which are often hydraulics or pump related. And then last but not least, we have this rubber hose, which is generally used for non-critical applications, a lot of times shop air, things like that. So looking at this chart here, this is interesting because it kind of just shows a general overview of the strengths and weaknesses of different hose types. So if you look here on this first one, we'll talk about metal core quickly. First of all, I should say green is good, red is bad, yellow is just okay. So a metal core hose has a wide range of temperature that it can handle. So it's good in that. It's good under pressure. It can actually go down to a fairly significant vacuum as well. But where the drawbacks are on that is impulse and dynamic bend, right? Where, for example, if you have a PTFE hose or a Teflon core hose, you're going to be much better in that dynamic range, and then also in cleanability, other things as well. So what this really illustrates is that you really do need to find the correct hose for the job. And you can kind of see here why that's important. And again, that's kind of going to be the theme of this presentation. So let's get into a quick case study to kind of illustrate that. So for this particular one, they were running hoses on a steam application at a tire press, which were failing in about 3 to 4 weeks, which is it's very frequently for hoses. Another key thing, it was a highly dynamic movement and it was tearing the rubber hoses. So if we go back one slide, actually, looking at rubber hoses, it's just okay in dynamic applications, and then also with steam, it's just okay under higher temperature ranges. So if you look over to the PTFE or Teflon core, it's better under temperature and it's much better under dynamic bend. So that would certainly be the hose to select for that application. And as you see here, they did select that. It was a little bit more expensive, but when it lasted more than 20 times, the 3-4 weeks that the rubber hoses were lasting, it certainly made sense to make that replacement. So here's another quick one. This is a biofarm application. First of all, I'll just kind of preface this and say that hoses are wear items. They're like tires on a car, they're like oil in your car. You need to replace it and you need to maintenance it every so often, or else you're gonna have failure, you're gonna be stuck on the side of the road, right? So in this case, they selected a cleanable hose and started a preventive maintenance program, which ended up saving them over 500K annually in downtime. So what they were doing was waiting for a hose to fail. They'd shut everything down, they replace that hose, and then keep doing that. Well, that's a lot of downtime where if you have a preventive maintenance program, you can just plan for that, shut the plant down, replace all these hoses, replace whatever else needs to be replaced, and then get it back up and running. So that can certainly save you a lot of money. So another thing from a safety standpoint, it's important to note that hoses are one of the most commonly handled items in a facility by techs, by operators. So it's really important if you have high temp or anything hazardous, you need to keep that in mind. And for example, you can throw insulators on there. You know, these are jacketed hose you see on the right. That'll prevent you from getting a nasty burn like this guy. Or else even just our S-series hose with that silicone layer can insulate that very nicely. So that's also very important. Let's see, real quick, let me just check, make sure we don't have any issues. Okay, good to go. So here's the next section. We're going to get into best practice as far as routing, and we're also going to talk about dynamic applications and anticipating that motion, kind of what to look out for, how to plan for it, and things of that nature. So if you look here, you see a bunch of kinked hoses, which is not good. There's a variety of ways that, things that you can do to kink a hose. But it's very easy to prevent as well. So we'll kind of talk about how to prevent that and talk about best practices here. So first of all, just the background, a kink is just where you bend a hose beyond the minimum bend radius. It causes permanent damage to the core of that hose. It's not going to look the same. It's also not going to hold the same pressure that it could initially. So you really need to replace it right away. It's just often caused by incorrect routing. So the important note on this slide, and if you're listening to this slide at all, take this away from it, is that we have all the minimum bend radiuses of these hoses in our catalog. And if you don't want to look in our catalog to find it, just give me a call, give your salesperson a call, and they'll be happy to find that information for you. So here's a similar slide, although I'm going to highlight on this slide, this middle picture here where you see the recommended. This has this 2 times the OD minimum straight length. So you need that coming off your end connection, just so you're not straining your end connection and kinking at your end connection. I mean, if you look here on the right, this comes right off the end connection and bends pretty sharply. Well, that's going to cause a ton of strain, shear stress too on your end connection. It's going to kink there, and it's going to ultimately fail there. And you see the same thing on the left, actually. It comes off and it comes straight down. So you actually don't have the minimum bend radius and you don't have the minimum straight length, which is, kind of a double no-no there. So what you really should do is just add an elbow adapter, have this coming down, and you'll have a happy, healthy hose. So this slide just emphasizes that, we just talked about minimum bend radius. It gets emphasized when you get into dynamic applications. Dynamic applications are just tougher on hoses in general. So if you have a sharp turn and you're not sure if you should give it more give, first of all, do it just so you're not, you're taking it easier on that hose. Second of all, we do also have dynamic minimum bend radiuses in our catalog that you can pull. So if you're having routing issues, you're questioning yourself, pull it, or like I said, give us a call, and we're happy to pull that information for you. So here's just another one about using adapters. weight of your hose can certainly cause issues as well, especially if you're running a liquid through there. So if you look on the right picture, if this was filled with liquid, it's going to be pretty heavy and it's going to pull pretty heavily down right at that end connection and cause some good shear stress there. What you can do is just add an elbow adapter, like we mentioned on the previous slide. That'll make this hose much healthier, and that hose will last a lot longer. And it's the same thing on the left here. You see this picture, comes off, comes to the left, goes down, comes back to the left. You just add an adapter in there, an elbow. It's going to be much easier on that hose near the end connections. So here's a really important one too. This is, so bending a hose on multiple planes. Really what we say is, if you bend a hose, you should be able to either place that bend on a table flat or against a wall flat, and that's kind of how you know you're bending on one plane. For this example, you see this picture on the right. This hose goes up, it goes over, and then it comes back, right? So this is also a dynamic application. So as this goes back and forth, it's really going to cause a lot of twisting stress, and it's going to cause, there's going to be tons of internal stress in that hose just throughout, and especially at the end connections. So that hose is going to fail pretty quickly, and it's unnecessary because you can really just put a static hose here like they did, and then put another hose here that's going to feel that dynamic movement, but then they just add an adapter there. So certainly this setup on the left will last a lot longer. Okay, now we're getting into some static dissipation. So static buildup in hose is an issue, and it's similar to, you walk through the door, you take your fleece off, you touch the door handle, and you get shocked, right? It's this very similar concept. It's actually the same concept, and you see here in these regular Teflon core hoses, they're very good electrical insulators. So when you have a media that can generate this electrical charge, this static electricity, it just kind of builds up and sits there. So it builds up to the point to where it jumps to the nearest conductor, which is often a stainless steel braid on these hoses. And when that happens, you see these burn marks in these hoses. You see it on the left here and on the right as well. That looks to be a zoomed up image. But what that does is it makes little pinhole leaks. It causes failure. Those leaks can definitely propagate into bigger leaks. But more importantly, this static dissipation or the static buildup is often caused by non-conductive media, which is a lot of times hydrocarbons. So if you know anything about hydrocarbons, you know that you probably shouldn't have sparks near them, right? So it can also be a safety hazard as well. And here's just a few factors that affect static dissipation or static buildup. One being the conductivity of the core material, certainly, right? I mentioned that Teflon is definitely an electrical insulator, so it's going to be an issue with that. Conductivity of the media. So you see this list of medias on the right. These are really what you need to look out for, these medias. So if you have that, you should almost default to a static dissipative carbon core hose. Again, if you have any questions with it, come to me, come to your sales rep, and we'll be happy to help you out with that. And then a couple more, just velocity of the media, and then there's a few external factors as well. And it's a really simple solution to this problem, especially if you need a Teflon core hose. What we can do is we just have this carbon-filled, carbon-infused core in these static dissipative hoses. And what that allows for is that as that static electricity builds up, the carbon inside of it gives it just enough conductivity to take that charge and dissipate it along the end connections. So it really eliminates that threat. So another note is it doesn't affect cleanability. It doesn't really affect the performance of the hose. So that's why I say it's almost, if you're curious about it, just default to it, or else ask your sales rep, certainly. So this slide just illustrates the difference between static dissipation and conductivity. As you see on the right here, this metal core hose is very conductive. It's at 0.4 ohms of resistance, so that is a conductive hose, right? where you look on the left, even though this is a static dissipative hose with a carbon infused core, it still has 80 million ohms of resistance, which is a ton. So just because the takeaway is just because a hose has static dissipation and has that carbon core does not make it conductive. We do have a variety of offerings with conductive hoses, both with the Teflon core and obviously the stainless steel core. So just know that and know the difference and know when you need each. Stuck here. Okay, let's talk about permeation. So permeation in hoses specifically is where the gas inside of the hose sort of seeps out through the walls of the hose and into the atmosphere, where there's no real leak. It just finds its way through those walls. So where you really need to be worried about it is applications where you're working with a small molecule gas, such as helium or hydrogen. That's where you often see it. It can be a safety concern, and a lot of times it's just it can be expensive. You know, the gas can be expensive. And it's fairly preventable, so we'll kind of talk through this. Just a few factors that affect this. Surface area, certainly. You know, if you have a 2-foot hose, that's going to permeate more. Has that more surface area than a 1-foot hose, it's going to permeate more. Pressure, same thing. You know, you increase the pressure, increases the gas molecules, it's going to permeate more. Temperature, it's going to move the molecules faster, it's going to permeate more. And then wall thicknesses too. You know, the thinner wall you have, the easier it is for that gas to escape, which means that it will permeate more as well. So, and then something that often goes under the radar is the sintering method, which is sort of the construction aspect that we're going to talk about here in the next slide. But that can definitely affect the rate of permeation as well. So let's get into this examples here. This is actually a really interesting slide. A non-sintered hose, 1/4 inch at 3000 psi nitrogen, permeates about 150 cubic centimeters per foot per hour, which is roughly 3 golf balls. I looked it up. So at standard condition, that's about 3 golf balls worth of gas. So you compare that to a slow sintered core, same condition, same hose, or same length of hose, permeates 20 cubic centimeters per foot per hour. And then a post-sintered at the same conditions, 4 cubic centimeters per foot per hour. So the sintering process works like you get your core of Teflon, your Teflon core, and you kind of bake it. And you kind of bake it to the point where the pores come out of it. And what that does is it increases that wall thickness for that gas to go through. And as you can see, it really lowers the permeation rate. And it's also important to note that a lot of the market lives in this non-sintered range because that's what their cores are. Our hoses at Swagelok are in this slow sintered core to post-sintered. So we do have offerings in each. Okay, let's talk about metal hose. So as we saw in the first few slides, a metal hose, the inside of it is this corrugated, convoluted piece of stainless steel that's very flexible, and that kind of gives that hose the flexibility while also giving it that properties with having the wetted components be stainless steel as well. So the way this is made is you get this strip, you roll it, you weld it, and then you find a way to corrugate it. And there's a couple ways you can corrugate it that I'll talk about. And that's kind of what makes the difference in this hose is the corrugation method. So the first method is a mechanical forming method. So what happens is rollers, mechanical rollers, roll this tube to make these corrugations. And you can see here where these rollers would be contacting that tube in this picture on the left. So you really have high stress risers in the crest and the root here. What that does is it causes some work hardening, and actually it also imparts twist on the core tube, which can cause just some internal stress, which isn't good for your hose. Also, dye marks and scratches certainly go along with the stress risers. So the way we do it at Swagelok is we have this same core tube, we get to this sort of stage, and then what we do is we push it against the die, and then we compress a liquid against it, and it forms it against that die. So that's how our convolutions and corrugations are made. And as you can see, what that does is it really evenly applies this stress across each of the corrugations. And why that's important is it minimizes those stress risers, it minimizes work hardening, which is going to cause early failure, and it actually lasts 10 times longer in dynamic applications, which is fairly significant considering, hoses are often, that's kind of the point of them, is they're in dynamic applications. So disadvantage, it's a little bit more expensive to do it that way, but like I said, it lasts 10 times longer, so we see value in that. Okay, I think I'm going to went through that pretty quickly. Real quickly, if you guys have questions right now, jump over to the Q&A right now if you have questions, and throw questions in there. Or right now, if you want to as well, you can jot down my info if you have any questions you want to take offline. And I'll quickly summarize this. So if you take anything away from this, just understand which hose type you need for your application. First of all, break it down by the category, right? Do you need the Teflon core? Do you need the stainless steel core? Do you need a rubber hose, whatever? And then through that, you can kind of break down the different series. And it's very important to do that. But if you have questions on it, feel free to reach out to your sales rep, to me. I mean, I'm always open. Even just call the office, and you'll be hooked up with someone. And then once you have the right hose, you need a plan for safe and efficient routing. We saw all those mistakes. It can cause early failure, and it's just really unnecessary, especially when a lot of these problems can be fixed with just an adapter of some kind. 3, know when your hose needs to dissipate static. It's actually the #2 failure mode of hoses. So if you're concerned about it, you almost need to default to it, or just call someone, and we're happy to look into it. But that's certainly an issue that can go unnoticed. And then if we're not your supplier for hose, ask your supplier how their hoses are made. And if you have more questions on how our hoses are made, feel free to reach out to me. Feel free to reach out to your sales rep, and we'll be happy to talk about it.